Okay, we start up again. So now talking about grid convergence index. You find some information under material here. Procedure for and so on and so forth. Something stolen from Journal of Fluids Engineering. When you are going to write, say, an article and try to get it published with a numerical simulation, many journals, they now demand actually that you have such a study to sort of defend that, yes, my mesh is okay, or at least adequate. So down here you find sort of an old classic report, not that old actually, that will describe your GCI procedure. So you can have a read for yourself, but now let's go through this quickly. Say you have a problem and you try with the mesh. Start with the mesh. Okay. Then the first thing you're going to need here is sort of an representative cell size. And this one should then be in meters. So if you have it in a 3D case, then you see here, you take the sum of all your volumes and then you divide by the number of cells. Then you will have an average cell size. And then you take the cubic root of that one. Then you will have down to meters. If you do it in a 2D, then it's just an area. You add all the cell areas, divide by the number of cells, so you have an average cell area here. Take the square root, and then, yes, you have something in meters as an average cell size. Actually, you don't have to do this stupid calculations. I mean, if you you'll see later, we are going to take these H values and then scale them with another one, with another different mesh. And since your either total volume for your computational domain or your total area, that's going to be the same anyway. So that's going to cancel out no matter what. So it will actually be enough here just to use 1/n in both these cases. You don't need actually this volume of this area. So you can see step 2. You need at least 3 meshes. 3 is the absolute minimum. And yes, they should be sort of finer and finer. And we are then interested in sort of the ratio here between one mesh to the next. And that one would be given as this small letter r. So here you have the H for your coarse mesh divided by the fine mesh. So of course, the coarse mesh is going to be bigger than the fine one, so this R will be bigger than 1. And actually they recommend here bigger than 1.3. So when you say if you double your mesh in 2D, then actually you don't get 1.3, I think you get 1.2 something. So you have to sort of pay attention when you here play around with the different meshes. Check this ratio that it is bigger than 1.3. And also here I don't think they say it, do they? That it shouldn't be too big either. No, they don't say it. So I have seen reports when this one actually have been 3, 4, so it can be pretty big. But you shouldn't overdo it. I mean, then you will have a very coarse mesh versus a very fine mesh. Then these two solutions, they don't really talk to each other at all. Because I mean, the idea here is that Smaller and smaller delta x's should give a value that sort of should converge towards the correct solution. So if you have too big jump here, then that's not a good idea either. But at least bigger than 1.3, say up to 2, 3, something like that. So here now, as I said, you need 3 meshes. Here they have done it with just 3 meshes. So you have H1, 2, and 3, and then you have 2 different small r's as a ratio between these cell sizes. And then, important, you can calculate the apparent order. And that one is quite crucial for this procedure. If that one is not, say, close to the actual order that you have in your numerical scheme, then there's something very, very fishy going on here. So that one has to be, say, close to 2. How to find that one? Well, you actually have an implicit equation set up here. You will have the order here and you have the order here, so you have to use some numerical solution for this equation system to actually find the P. Now, the important thing, very important thing, the value that we are looking at, here they have just said phi for the different 3 meshes. That one is a monitor. That is something that should, say, be maybe your main result, your main variable, your main question mark in my simulation. But finding a decent value here, that can be tricky. So, as I say, a good monitor, well, yeah, we should actually have a look at that one. Say as an example, phi monitor sort of should be a sensible parameter for your solution. And how to find that one? Say now, our case that we had, you have a symmetry plane, and then we had a backward facing step, something like that. Sending in something here, and we have something going out on the other side. We have this nice vortex here, something like that. What is a sensitive monitor for this simulation? Say now, if we do the following. Here I now send in a constant velocity, flat velocity profile. If I don't use this special inlet condition, just send in a constant velocity. If I, as a monitor here, I choose the velocity at this point, that is really stupid. If I use the velocity here, whoops, did I remember to switch on the camera? I hope I did. Yeah, it's recording. If you choose that one, then you probably will find that your apparent order of your numerical scheme is 10 or 20 or something totally insane. Because you'll get the same value here no matter whatever mesh you have. You send in a constant velocity. I mean, it takes some time for the boundary layer to grow here. Well, it doesn't grow up there actually. So the velocity here is going to be the same, independently of your meshes. It makes no sense at all. It's not a sensitive monitor. Totally stupid. Don't choose that one. If you take a velocity, say at a given point over here, not so sensitive for this problem, is it? I mean, the essence, the important part in this problem, that's actually this reattachment zone behind the step. So if you then had taken a velocity at a given point, maybe somewhere here, that might be okay to use that one as a monitor point for the velocity. That could be okay. In this article, with the description of this grid convergence index procedure, they have actually used this as an example. What do you know? And what did they choose as a monitor? The reattachment length. This XH scaled with the step height. So they used that one as a monitor. Why not? And as you saw from my solution for exercise 2, yeah, it's pretty sensitive. It changes all the time when you change the turbulence model or you change the mesh or whatever. So not a stupid choice. He describes sort of the physics quite nicely. Good choice. Good monitor. Bad monitor. So you see here, when you do this procedure, you may have to look at 3 different simulations, 3 different solutions on 3 different meshes, and then start looking around for a good monitor. You may try several times actually before P is around 2. That is good monitor. And it should. So I would accept 1.5 to 2.5, somewhere in between that range. Then it's okay. Then you can use that monitor and then continue with the procedure. If you don't get it, then try to find a better monitor. If you still don't get it, you have to create 3 different meshes. Maybe you have done something stupid with the meshes. So, tricky things. Any questions to that one? Find a sensible parameter. You only need one parameter. You can't use a whole profile here or something like that. So just a single point. You may, here for this problem, that could be an idea. Say we are sending in a constant velocity here, or a given velocity. What is the driving force in this problem? Who's doing the job? Well, clearly that's going to be the difference between the 2 pressures. So yes, you could have used the pressure gradient, an average pressure here versus the average pressure at the outlet, and look at that difference. That's a driving force in the problem. Of course, that's also sensitive, because this driving force sort of has to balance all the resistance inside, say, the computational domain. So yeah, that might also be a good monitor. I don't know, I haven't tried it, but okay. So inside here we have some small epsilons. These epsilons, they will then be the difference between these monitor values for mesh number 1, 2, and 3. And there also you see, if you choose a bad monitor, like the first one I suggested, just a velocity just after the inlet, these are going to be 0. Then the entire thing breaks down. So then you can't find a solution at all. So you will rapidly see, oh, this is a bad monitor. Okay. Now, after doing this, we have the order P. Beautiful. Then we continue. Let's see now, as I say, the equation system 3, you have to solve it using something numerical. I used F0 in MATLAB. I'll give you the script, have given you the script already, so we can have a look at that one later. Okay. Now, we can actually find extrapolated values. Extrapolation, as you should know, is highly illegal. We're not allowed to do that. So finding a solution with 3 meshes and then extrapolate, what would it be if I have an infinitely fine mesh? That's not allowed. We'll actually get an idea here, but don't use them. But the values, of course, with finer and finer meshes, they should tend towards sort of a correct value. So they shouldn't sort of give something completely insane here. Then the procedure breaks down and you have to do it all over again, find a new monitor or something. So, but we can find them. And also we can get some ideas with the relative error, even for the extrapolated ones. And finally, here you have a recipe then for your GCI, the Grid Convergence Index. That one tells you what's the error for your solution monitor at the finest mesh. So that one is the one we are interested in the end. So I think they have something here. Yeah, we can take it later. That's also a point here. It would be very, very nice when you report something. You have a result here. This is my answer. Plus, minus. That would be nice. I mean, the guys in the laboratory, they have to do that. They have a lot of uncertainties in the measurements, and they should also be able to find a result, plus, minus something. What's the error for my measurements? We should do the same in CFD. This is the way to do it. This is the way to do it. So yes, using error bars, that would be beautiful. Not that many people are using it yet, but this is something that is really coming, and yes, it is important. Very important indeed. So here they have set up a table for us. So they have tried here with different monitors. It's the same problem as us, backward facing step. So here they have used the reattachment length. So with 3 different meshes. Here they have taken a velocity at a given point. It's roughly just above the reattachment length, I think. A little bit more to the right, maybe, yeah. And then here the same, but now they had oscillatory convergence, meaning you have your 3 values, but they are actually oscillating, still tending hopefully towards a steady solution. But never mind that one. But here, important point. You have your mesh, then you can easily calculate these small r's. You have your solution here, reattachment length for the 3 different meshes, and then you can calculate your P, the apparent order. This one should be close to 2. It's 1.5. But okay, I can accept that one. This one, out the window, can't be used. It's way too low, as it says here also. Apparent order is smaller than 1. Come on, that is not good. Bad monitor. Doesn't have to be anything wrong with your simulations. It's just a poor choice of, say, finding a monitor that is sensible to the physics in the problem. So, out the window. This one, better. This one, better. Let's just focus on this one. Now, having found the p-value, then we can complete the diagram, finding the final, the extrapolated value. So here is sort of tempting, isn't it? I have, this is my finest mesh, coarsest mesh. So you see the value here tends towards this value. And now if you extrapolate, I get this value, forbidden. Not allowed to extrapolate, you never do that. But it's tempting. Maybe this one is a very good result, so be it. You can report it, but then of course you have to say, this is the extrapolated value. What instead you should do, you take your finest mesh solution and you say, this is my answer, plus minus 2.2%. That is the way you should do it. So use the fine mesh solution, not the extrapolated one. A little bit dangerous, to say the very, very least. Okay, any questions to the procedure? Then we have something here. Let's have a look. Here they have taken a velocity profile. It must be, say, somewhat after the reattachment length, I think. So you are here at the bottom wall with zero velocity. And then you sort of have a rather flat velocity region up. Here you see also, it's not the same as the problem we had. We had a symmetry line at the top. Obviously, they have a solid wall at the top. So the velocity goes to zero up there. But here you then see our three meshes and then the extrapolated value. I think in grid number 1, that was the finest one. So the finest and the extrapolated, well, they are actually fairly close here. So how should you report your answer? Well, actually, you should report it like this. How to do that? Well, that the figure B there, that is your fine mesh solution here. But you see, for every point, we have added outward bars. How can you do that? We only had one GCI, and that was actually not for this velocity profile thing, but it was for the reattachment length. Well, if you want to do it like this, and I mean, this is very nice indeed, this is the way it should have been done, but to find it, you actually have to use your GCI procedure for every single point where you want an outward bar, because you have to find the local outward at that point for that monitor value. So you should do it for all the velocities. And this is rather boring, to say the very least. Of course, you can write a script to do it, but normally when you sort of are aiming for something like this, for a profile, then we cheat. We cheat. You take, well, first of all, you have to decide where you want these outward bars. Then you simulate with 3 different meshes, and you detect the velocities at these locations on all meshes. So, I mean, you shouldn't have too many. Here they have overdone it a little bit, I think. So that might involve a little bit of interpolation, because you need the exact same location for all 3 meshes. Anyhow, when you have the velocities for all 3 meshes in all these points, you can evaluate the local small p, the order of your, the apparent order of your numerical scheme. You will get a different value for all these points. And then we cheat. We create one average value, and then we have 1 p. Done. So that is the way you create a profile. That makes life a little bit easier. I think they explain it somewhere here. Yeah, and then of course this p-values, they actually had a nasty range here. As I said, it should be close to 2, but that is if you have a decent monitor. When you have the different velocity points, of course some of them will be rather bad monitors anyway. So here you will accept that this one is far away from 2 as it should be. That's okay. But you see they just create an average apparent order. Even that one is, say, a little bit too far away from 2, but that's okay still, because we know these are bad monitors for, say, given the physics in the problem or describing the physics in the problem. So that's okay. But doing it like that, yes, you can find your different error bars very nicely indeed. So this one, if you can produce velocity profiles like that with error bars, oh, you get a star in the report there. I think they had something more here. Yeah, that's a different location. I think this one is closer to the, or inside the reattachment zone. You see the initial velocity here, he goes negative. So clearly you are inside your say this recirculation zone. And you have a whole bunch of references. But I mean, this article here is now widely used worldwide. So yeah, you can use this one as a reference. It's well known. Let's have a look at how to calculate this thing. First it was the small h, then it was my small r, the ratio there, then finding the monitor values, calculating the apparent order, and then finding the error estimates. Let's see now. It should be here somewhere, I think. So, under learning material, you find this article, and also you find a small MATLAB script, which I now will show you. I have 2 MATLABs. Ah, never mind. He can handle it. Let's try to open that one. Oh, maybe he didn't like 2 MATLABs. It doesn't look like it. Not responding. Let's try to crash him. So let me try to open it here instead then. Where are we? Here and GCI. So this one, just a cute little MATLAB script. And here I've just taken the numbers from this article. And here also you can see I did the dirty trick. This was the monitor values that they displayed with finer and finer mesh. Here was the number of cells. But first of all, square root, because it's a 2-dimensional thing. If it was a 3D, you had to take a cubic root here. And then you see I just take 1 divided by the number of cells, because what really should be here should be then the total computational area in square meters. But since we are going to divide them anyway, this number by this number, it doesn't care. He will be cancelled out anyway. So the only reason you want to use, say, the total area here, is that you want to have this one in meters, so you can have a sort of an idea what is my average H here. Of course, if you have uniform cells all over the place, then you don't have to do this at all. Then you know your delta x. If that one is equal to delta y, then If that's constant, no problem. Then you have the number already. Then you don't have to do it, of course. Anyhow, here I just punched in the R values as they reported. And then we have some calculations here. To find this apparent order P, yes, you have to solve it numerically. So here I just use P0. Just I create a function. That was this equation 3 in this article, which consisted of 3 parts. I just glue them together, and then writing it on the form equal to 0. And then he should find my apparent order P. And then you can find these extrapolated phi values, which never should be used. And then the errors, and then finally the GCI. So if we run this one, let's see. We should get some results here somewhere. No, we didn't like that one. Ah, my mistake. My mistake. I can't have GCI as a name of a variable. Okay. And let's call him something else. GCI underscore. Then we get it. So here then, you sort of have all the numbers you need. I got a P, same as they got in the article. You have the extrapolated values, the error estimates, and finally down here now, the GCI, 2.2% of my monitor value. So you should then, if you write an article, give this table, as they have done it in this article, as a part of your, say, report. Or at least, if you don't have space enough for the entire table, at least then explain how you've done it, what monitors you have chosen, and then definitely you have to report what value did you get for this apparent order. If that one is not close to what you actually have, then you're in trouble. So 1.5 to 2.5, somewhere there. So report that one, and then of course report the plus minus for your actual answer in the end. So that is sort of the setup for a GCI. You have it on the home page, so it shouldn't be too hard. Any questions to this one? That's okay. So let's go back to the upcoming exercise 3, first report exercise. Now what should it contain? What is our theory that we have sort of struggled with the last weeks? Of course, turbulence models. And we have, say, stopped at the Rans chapter, or say, description, 2 equation models, or maybe even 1 equation models. We have something called Spalar-Alamaraz as a 1 equation model, 1 transport equation model for the eddy viscosity. That's also something you should be aware of. For now, we have just played with typically k epsilon, k omega. So that one is something definitely that should be part of your report. Convince me that you know how to use these. And also then, what is y plus? Why do we need that one? What do we use it for? Important. And also then the law of the wall. That's also something we are using. I mean, they are connected, sort of decides should you use a model as a function towards the wall, or can you use natural boundary conditions for your turbulent quantities? Very, very essential. And now you have learned about GCI. Also something that should be in your report. What kind of problem are we going to look at? Well, I think I'm going to do the following for you. You should find this later today. Say now here you have a pipe. Here, all of a sudden, you have an expansion of the pipe, something like that. And somewhere here, it goes back again. So you have a contraction to the same original diameter that you started with. And then we send in something here. And of course, you should get the same out on the other side. This is your job. Now, to do this one in full 3D, that's quite heavy. And using, typically here you would use cylindrical coordinate systems, is rather messy. But we don't need it. This problem is axis symmetric. So we put in, not a symmetry line, symmetry plane, but a symmetry line along the center, like that. And then we take a small piece of cake of the entire problem. So you'll have a mesh system that actually will look something like this. Small cake, and then he will go something like that. And then you will go a little bit further out, continuing, going down again here, and then continuing finally. So you'll have a mesh system looking something like this. I will give you such a mesh. I will do it quite crudely. So obviously then you have to change the dimensions here to get a reasonable simulation out of it. But I just give it to you as you see how such a mesh can be used. Normally they say this angle here should be quite small, 5 degrees or even smaller. So if you overdo it, then it won't be representative anymore. Because here, of course, nothing is going here in the theta direction. You only have in the radial direction, like that, and in the axial direction. So it's a two-dimensional setup. That's a standard way of doing it. So you have a lot of questions to answer when you are going to start to simulate something like this. First of all, it better be turbulent. You have to ensure that the Reynolds number is high enough. So critical Reynolds number for a pipe flow, 2100. Your choice where you put your Reynolds number. You can take it quite low, 5,000 or something. Or you can take a medium Reynolds number, 50,000. Or you can take a big one, 100,000 and 1 million. Your choice. So I'm not going to influence you how to do this. You have to choose different parameters yourself. Okay. Then of course you have to find a decent mesh. I just give you here the recipe how you write such a wedge mesh. So you have to fight with that one yourself, finding a decent mesh. And you also need to find decent values for the different diameters and the different lengths. So say what I want is a fully developed turbulent flow that hits here the expansion. Then I want a fully developed turbulent flow hitting the contraction. Then I want a fully developed flow hitting the exit. So some elements you have to try to recall from your kindergarten course in fluid mechanics. Fully developed. Fully developed flow. Then how can you decide when the flow is fully developed? You have something called an entrance length. This is something you have to address. The entrance length, of course. And also, as a final result here, when you have done this simulation, you can think in terms of, say, the driving force throughout your entire domain. Now, you can either take, say, an average pressure at the inlet here and at the outlet, look at the pressure difference. That one should be close to what? Well, it's a fairly simple geometry here, and if you can recall kindergarten, yes, we had something with Bernoulli with losses. So here you're going to need Bernoulli with losses. And losses, what we did in kindergarten, at least in our university, we split that one in two. You have major losses. What was that? That was the friction, the viscosity. And then you had minor losses. Minor losses, that was losses due to, say, change in geometry. If you have a pipe bend, if you have an expansion, contraction, you had different types of these minor losses. So of course, as a, say, final solution, I think your simulation, whether you use just the pressure alongside this symmetry line, it's actually okay. The pressure doesn't change much in the radial direction anyway. You can create an average pressure at every, say, streamwise location here, but it's actually not necessary. So that should sort of be your main result, and then he should compare favorably to this one. Although Bernoulli with losses, that's an engineering tool. So they say typically plus minus 10%, 15%, and then it's still okay. So it's quite crude. But at least they should sort of be of the same order, or else you have done something very, very wrong indeed. So and this should be your task. I'll write this one up for you as an exercise 3 description. And as I said, the important thing for you is not to write a nice report. The important thing is to show me you have understood this. That's the important part. And in the end, if you get a bad result, that's okay. As long as you describe how to get a good result and you can explain why you didn't got a bad one. Because you couldn't afford the number of cells or your PC broke down, I don't know. That's not the important part. The important part is convince me that you have met the learning objective in the course. Then this one is the important one. Yeah. Yeah, as a template, I would say my solution for exercise 2. I mean, you don't have to write entire sentences even. You can just use bullet points, and that's okay, as long as I can understand what's there. I mean, in the exercise hours to follow, just ask me, is this okay or not?
Is it supposed to be similar to the project you had in the intro course?
No. That project in the intro course, that was much more heavy. I mean, that was half a semester, for crying out loud. Now you have 1.5 weeks, so keep it short, brief. And you can think in terms of, if the other in the class can understand this, then it's good enough. Then probably I can understand it. Yeah. Other questions? Then we stop here.